Hello everyone. One of the most important building blocks in MobileNets, in both MobileNet version 1 as well as in the second version, is something called depth-wise separable convolutional layer. So this depth-wise separable convolutional layer is very important and makes MobileNets very fast. But to understand, or before explaining how such building blocks work, it is necessary to review the standard convolutional layers. So what I'm going to do in this video is to first give you a recall about standard convolutional layers, and then estimate the computational cost of such layers. And this is important because later we will compare this computational cost with that of depth-wise separable convolutions, right? So we would have the computational cost x1 of standard convolutional layers, then the computational cost of depth-wise convolutional layers, and we would compare them with each other to see the advantage provided by depth-wise separable convolutions. Well, let's start by exploring the major steps or the main steps in a standard convolutional layer. So we have in general 3 steps. The first step is called convolution. Second is batch normalization, and the third is application of a nonlinearity function or an activation function. So we usually use ReLU, and in MobileNets I think they use ReLU 6. Well, as an aside, in recent CNN architectures we do batch normalization at each layer, whereas in previous older architectures we do batch normalization only once at the input of the model, right? Anyways, what I'm interested in is this step here. So at this step what happens is that we take an input f with the following dimensions. So let's say, so I'm using the notations from the original papers, so it would be easier for you if you want to go and see more details. So in the original paper they use the notation f for the input to this convolutional layer, or to this convolutional step, right? So the input has the following dimensions. It has a width, or rather a height of df, a width of df, and the depth or the number of channels is equal to m, right? And we get at the output of this step something called j. So this is the output, this is the notation of the output. And before telling you the dimensions of this output, it is important to specify some hyperparameters of the convolutional operations. So I assume, or authors assume, that at this step here the convolution uses is stride of 1 is equal to 1. So this means that each convolutional kernel moves by 1 pixel, right? And the convolutional operation is a same convolution. What does that mean? It means that the spatial dimensions of the output is equal to the spatial dimensions of the input. For example, here the spatial dimensions are df times df. When we use same convolutions, then the spatial dimensions of the output should be also df times df, and this requires something called padding. if you don't know about this, please go and watch some YouTube videos about this topic. There are tons of videos. Whatever, my purpose here just to give you a recall about these things. And now the number of kernels used, we assume that the number of kernels used is equal to n. And since each kernel produces one channel when convolved with the input f, then the number of channels in the output should be equal to n, right? So now let's talk about some details about the kernels use. So the kernel use, we assume that we use n kernels, ki, right? So I, this is just the index of the kernel. This means that I starts from 1, 2, and so on, and the last number in I is n. Also, we assume that the spatial dimensions of the kernel, or the dimensions of each kernel, ki, is dk times dk times m, or rather n. Sorry, it should be m, yeah, because the depth of each kernel should be equal to the depth of the input, so this is necessary, right? And this is valid for each I. Now, when we convolve with ki, with n kernels ki, we say that we convolve the input f with a kernel k, capital K, such that k is a 4-dimensional tensor, and here are the details of its dimensions. So we have 4 dimensions. The first 2 dimensions are the spatial dimensions of each kernel. Then we have the number of channels of each kernel, and then we have the total number of kernels, right? So this was a recall. Now what I want to do is to figure out the computational cost of after convolving all of these kernels with the input f. So to make things easier, I've prepared this visual representation. So I assume that I want to convolve a 9 by 9 input with a 3 by 3 kernel. So of course I have n kernels. Each kernel ki has the following dimensions. So it should have 3 times 3, and of course the depth or the number of channels should be equal to the depth of this input. So I assume that the depth of this input is m, and this means that the depth of each kernel is also m, right? So here normally we have padding. This input is padded by zeros, right? So we have zeros here. Now, when we compute the computational cost of the convolution operation, usually we focus on we estimate the number of multiplications, or we compute the number of multiplications. So the computational cost is equal, C is equal to the number of multiplications. So at this stage, you might be wondering, why we do not include the number of additions? Well, the short answer to this question is because the computational cost of a multiplication operation is much higher than the computational cost of additions, especially if we are multiplying large numbers with each other, right? So this is why we focus just computing the number of multiplications to figure out the computational cost. Now, what is the number of multiplications? Well, first of all, the number of multiplications should be equal to the number of elements in each kernel. So it should be equal to the number of elements for each kernel Ka, right? Because we are doing multiplication wise in each position. Then we need to multiply that by the number of kernels, which is n, right? And now each kernel performs this multiplication wise how many times? Well, it performs multiplication wise at this first position, and then it moves to the next position, third position, fourth position, and so on until it gets here, and then it goes to the next row, right? And so of course we go 1 pixel at a time because we have a stride of 1. What does that mean? It means that we should include the total number of positions taken by each kernel, and the total number of positions taken by each kernel is 9 times 9. In other words, it's df times df. Well, anyways, we should multiply that by the number of positions taken by each kernel ki, right? So this is the computational cost. Well, given the notations we have, the number of elements of each kernel ki is equal to dk times dk times m. This is something that I just explained. So I said earlier that the dimensions of each kernel ki is dk times m. Therefore, the number of elements in each kernel is dk times m, multiplied by the number of kernels, which is n, then multiplied by the number of positions taken by each kernel. So in the case when we have a stride of 1 and same convolutions, this thing here is equal to df times df, or 9 times 9 in this specific case. So it's dk squared times df squared times m times n. So this result here is important, and we will later compare it with the computational cost of depth-wise separable convolutions.